Hello, this is Hui-Ju from the Penn State University. Today, I'm glad to have this chance to present our work, Efficient Algorithms Toward Network Intervention here. This is a joint work with the De-Nian and National Tsinghua University. This work starts with our interest on relationship between the well-being of an individual and the social relationships surrounding the individuals. For example, a work published in Science indicates that the relationships surrounding individuals have a substantial impact on individuals' mental and physical health. Specifically, socially isolated individuals are more inclined to have mental health problems and physical disease. In existing work on psychology, a possible way to improve the well-being is network intervention. More specifically, network intervention is to introduce new relationships or new social links to individuals. The new links are generally built by frequent interactions like curative grouping and network meetings. However, an important question we want to ask here is how can the link be chosen appropriately? Generally, these links should be recommended by specialists or practitioners. However, specialists and practitioners are also persons. They have limited time and limited resources to review the data and provide recommendation. In other words, it is impossible for them to examine every candidate. Also, the recommendation made by persons may have subjective biases. So, it will be helpful to have an automated network planning algorithm that can simultaneously consider and optimize multiple network measurements. So here comes the next question. What kind of network measurements can be adopted here to provide the supplemental objective information? We list four possibilities from literature: degree, closeness, betweenness, and local clustering coefficient, or LCC. Individuals with a large degree is more inclined to be popular and to have more opportunity to establish self-identity and social skills. Individuals with large closeness is typically located in the center of network and tend to perceive a lower level of stress. Individuals with large betweenness occupy broad-edge positions in the network and perceive social relationship and the events happen in the social network accurately. Individuals with a small LCC tend to have diverse relationships and is less likely to have mental health problems like depression. Among the four measurements, the higher the degree closeness and betweenness are, the better the well-being is. The lower the LCC is, the better the well-being is. So in this paper, our goal is to develop this kind of automated algorithm that consider LCC, betweenness, closeness, and degree simultaneously. So what will be the challenge if we want to achieve the goal? The first challenge is there will be a large number of candidate age to be examined. Second, even though to optimize the degree is in polynomial time, but it is NP hard to optimize the betweenness, closeness, and LCC. Among the three, LCC is even more challenging. Adding an intervention age may worsen the LCC that not only involve in the individual, but also others in the network. For example, consider the small network in the left-hand side graph. If we add an age between B and G, the LCC change is labeled in red, and you can see even though the LCC of B is reduced, the LCC of G, another involved in the intervention age, and C, which is not even involved in any intervention age, are both increased. So, aiming at this, we formulate the first problem, NILDS, the intervention for a single target. Given a social network G, the target T, the number of age to be at K, the LCC degradation threshold tau, and the lower bounds of betweenness, closeness, and degree omega B, omega C, and omega D. NILDS ends at finding K new age F to be A such that the LCC of the target is minimized. The second, for all nodes in the network, the increment of LCC should be less than tau because we don't want to worsen the status of others in the network. Third, the targets betweenness, closeness, and degree should be larger than omega B, omega C, and omega D respectively. We prove that NILDS is NP-hard and cannot be approximated with any ratio unless P equal to NP. We prove this by a reduction from maximal independency problem under triangular free graph. Even though NILDS is NP-hard and cannot be approximated within any ratio for a general graph, we prove that NILDS can be solved in polynomial time if G is a threshold graph. Threshold graph is a spatial graph that shares many similar structural properties with online social networks. The formal definition of threshold graph is, for a graph G, it is a threshold graph if there is a weighting function f and a threshold Tg such that the H only exists if and only if some of the node weights exceed the threshold Tg. Here we show an example of threshold graph. Here, the node weights associated with V1 to V7 is 1 to 7. And this is a threshold graph because only H only exists when its sum of the node weight exceeds the threshold. We propose CRPD algorithm for NILDS. NILDS includes two main concepts, RNR and MIS. RNR includes a basic greedy, which iteratively selects the node U with the least degree to connect with the target T. Then it removes the nodes V if adding H, TV will violate the constraints. RNR is proposed to re-examine the removed node V to avoid missing good candidates. NISS is proposed to satisfy the constraint of betweenness, closeness, and degree. When there are multiple choices available, we choose the node U with higher betweenness, closeness, and degree to connect with T. In addition to the scenario to intervene a single target, we are also curious about whether we can make intervention for multiple targets. So the formulation of NILDN is this as follows. Given a social network G, a set of target T, the number of H to be 8K, the LCC degradation threshold tau, and the lower bounds of betweenness, closeness, and degree omega B, omega C, and omega D. NILDN aims to find K new HF to be added such that first, the maximal LCC of nodes in the target state is minimized. Second, for all nodes in the social network, the increment of LCC should be less than tau. Third, for all the targets in T, the betweenness, closeness, and degree should be larger than than the lower bound omega B, omega C, and omega D. Similarly, NILDS NILDN is also NP-hard and cannot be approximated within any ratio unless P equal to NP because NILDS is a special case of NILDN. We propose OISA for NILDN. OISA includes three concepts: EORE, PONF, and LLC. EORE decides multiple target objectives to be tried. For each objective, EORE obtains a lower bound of required age. In other words, if the lower bound of required age is larger than K, this objective cannot be achieved by KH, so we don't need to run the age selection process. The age selection process, PONF, considers the optionality of nodes. While adding new age, OISA always start with the node with less options. For a node V, its number of options are the number of nodes such that adding an age between V and the node may not violate the LCC constraints. Similar with CRPD, if there are multiple candidates, we choose the node U with higher betweenness, closeness, and degree to connect with the target. The last concept, ALC, is to accelerate the LCC update after deciding new ages. OISA stores an upper bound of a node V if KH are added. During the update, OISA only updates the node V whose neighbors are involved in the new age, and the LCC of V is large enough to either violate the LCC constraint or V has the possibility to be the next target N to be extended. Our experiments include both simulation and empirical study. In the simulation, we adopt two datasets, CPEP and Flickr. CPEP contains 10 small social networks collected in the classroom of elementary schools in Pennsylvania. On average, there are 22 students and 58 aged before interventions. Flickr is a large online social network with 1.8 million users and 22 million aged before intervention. In the simulation, we compare CRPD and OISA with the following baseline. BUN selects large LCC node to connect with targets. SIN selects far nodes from the target to connect with target. In none, generally try all combinations. EA and TEA are existing work to improve centrality measure like closeness and betweenness. And GD is a greedy algorithm that adopts similar concepts with social inference maximization to make intervention. We test CRPD and baselines on various K, where K is shown in the percentage of the number of candidate ages. As shown in the figures, the performance of CRPD is close to the optimal solution obtained by Inan, and CRPD outperforms other baselines. In addition, CRPD is efficient in running time in comparison with other baselines on large dataset Flickr. Similarly, we compare OISA with baselines. The K is also shown in the percentage of the number of candidate age. The target T includes 20% of nodes with large LCC. The simulation result shows that OISA has similar performance with the optimal solution in none with much smaller running time on CPEP. OISA also scalable to large dataset and outperform other baselines in Flickr. We conduct an empirical study involving 424 participants aged between 18 to 25. In the beginning, before intervention start, there are totally 638 friendship links among the participants. We adopt 4 psychological questionnaires for well-being: the BAI for anxiety, the PSS for stress, the PNAS for emotion, and the PWS for well-being. For the first two, anxiety and stress, the lower the score, the better the well-being. For the following two measurements, the higher the score, the better the well-being. The participants are separated into 4 groups equally, so each group have 103 participants. We do a pretest to ensure there is no significant difference among the groups in the beginning of the test on the scores of all questionnaires. Among the 4 groups, 3 of them are the intervention group, whose new age are addressed by OISA, GD, and BUN respectively. Participants who are involved in the addressed age are asked to keep interaction for 8 weeks via online chatting, and the parameters are listed as follows. The first group is the control group. There is no intervention for the group. No matter the participant is in the control group or intervention group, they are all need to fulfill the 4 questionnaire every week for 8 times. So the study is totally 8 weeks. Here we show the empirical result of empirical study. The overall result is the improvement of the 4 questionnaires as shown. OISA has greatest improvement on the score of all questionnaires. And let's take a closer look to anxiety and emotion. On the top of the 2 figures, we group the participants according to their LCC change. The results show like the improvement of anxiety and emotion are larger for participants with large LCC decrements. On the bottom 2 figures, we show the average score of anxiety and emotion over time. In the following, we exploit mixed effect modeling to validate the effects of intervention by statistical methods. You can think this method as a regression. Specifically, the model we are going to fit is here. The HI is the score of individual I at the time t. The intervention I indicate whether the individual I is in the intervention group or control group. The time is the number of weeks passed since the study starts. The beta 0I is the random effect in intercept at time 0. The beta 0 to beta 3 is the regression weight we are going to fix. And the epsilon IT is the error. For each intervention group, we want to compare the result of the intervention group with the control group to see whether the intervention suggested by an algorithm is effective or not. Aiming at this, we fit the shown model in the previous slide to obtain the weight beta 0 to beta 3. Among the fit weight, if beta 3 is statistically significant from 0, it means that the intervention can change the outcome substantially over time in comparison with the control group, which means the intervention is effective. So here we show the result of OISA on the top and the result of GD and BUN on the bottom. Here the estimate values of beta 3 is all non-zero, no matter for every measure, but only the beta 3 estimate of participants in OISA are statistically significant from 0. So the results show that the age suggested by OISA is more effective than GD and BUN from the view of statistics. I will conclude my presentation here. Currently, no effective planning tool for practitioners to select suitable intervention age for network intervention. We formulate NILDS and NILDN for this need. We prove that the NP hardness and approximately of NILDS and NILDN and propose CRPD and OSA for effective age selection here. Experiment results and empirical study demonstrate the effectiveness and efficiency. Thanks for watching. Is the end of my presentation. Feel free to drop me an email if you have any questions.